Welcome back, everybody. So let's continue. I also wanted to try something from now on. So you notice that, so in the lecture hall, we have now the hand microphones because we clarified with the Corona team that it's fine to circulate them. On Zoom, it's the same. If you would like to speak over your microphone rather than writing, you can just raise your hand. It's probably somewhere like here. You just click on reactions and then you click on raise hand, and then Dan will see you and we can unmute you and let you speak. All right. But you just need, oh yeah, just to clarify, this is recorded. This is on YouTube. So if you decide to raise your hand and speak, then this is that you agree that this will be on YouTube, right? And otherwise, you can just write on the Zoom chat, and that's of course fine too, right? Okay. Having said that, let's continue. So let's look now into B trees and B plus trees. This is something that should actually sound familiar because this actually is the same things we use in relational databases as well. Surprise, surprise. I told you it's a database lecture, right? So how do we go from binary trees to B trees or B plus trees? Well, the key is that instead of limiting the number of children to just 2, that would be the strictly binary search, we can allow for more children. The reason why we actually do that, allow for more children, is that the nodes there are bigger and we can even group on the leaves. So the consequence is when we read from the disk the index, because that actually might be very large. You know that on the disk, we read in blocks, right? We like to read, for example, in blocks of 4 kilobytes at a time. We don't read bit by bit from the disk. And in order to optimize all of that transfer from the disk to the memory, what we like to do is make sure to size these things so that it roughly corresponds to 1 block. And that means that when you read it from the disk, it's not more expensive than if it had been a binary tree. So this is the reason why we actually do like to have more than 2 children and to design the trees in such a way that it's block access friendly. Right? So this is again something that we love to do on the database side of things, because when we have databases, we want them to be fast, right? So we want the index lookups to be as fast as possible. It will not change the complexity, but it will change the constant in front of the complexity. And the constant is actually sometimes very important, just as much as the complexity itself. So what happens then if we allow more children is that we need, of course, more than one lookup key in there, right? So here we have, for example, com, everything before that is here, between com and is there, between is and merely is there, and after merely is there. And that would be before between merely and possess, right, would be here. So this is the idea. That's what we call a B plus tree. B tree is the generic name for this sort of structure that are block friendly. What is the plus for in there? The plus actually means that we only have the actual terms and the posting list on the leaves. This is the plus. This is what it means. If it were just B tree, then we would also have posting lists in there. We could have the terms absolutely everywhere, right? So again, B plus tree means all the vocabulary is there and all the keys that are there are purely for lookup. And typically we just repeat the leftmost one, right, in there, right? Com, almost. So we possessed comes from here, that comes from here, and so on. All right, B plus tree. So what characterizes a B plus tree? Well, I have to give you a big warning. I have to give you a big warning is that this is not something that is fully standardized. And if you look that up either in textbooks or on the internet, you will find plenty of flavors of B trees and B plus trees. They don't look the same. They don't follow the same conventions and so on. So it's a bit of a mess, right? It doesn't really matter because in the end, when you implement the system, the user doesn't know which flavor you use, right? It just needs to work, right? But there are many flavors, there are many conventions. So of course, I'm going to stick to one single convention for the purpose of the course. But I have to warn you, if you try to look it up somewhere else, you might find that the conventions are going to vary a little bit, right? So just this warning. All right, so in a B plus tree, all leaves are at the same depth. You cannot have the leaves here and here. It's all at the same depth. That case, depth 2, right? So That's the first condition. The second condition in a B plus tree is that there is an interval on the size of the nodes. And typically that interval is given in the number of children that they have. For example, you could characterize a B plus tree as a tree with these parameters, right? Between 3 and 5 children per node. So 3, 4, or 5. So here it's 4, that's fine. Here it's 4, that's fine. And here it's 2, that's fine. Well, that's actually fine because it's the root, and the root has basically the freedom of being less, right? It's the only exception. So basically, I repeat, between 3 and 5 children everywhere. And for the root, it's fine if it has less. So it's between 1 and 5 between 2 and 5, because 1 would be ridiculous, right? So the root is the only one that has the exception, and that can be smaller, but it cannot be bigger, just smaller. All right. Now, since we limit the number of, yeah, that's what I wrote here, just so you have it. It's fine if the root has less. Now, the actual terms here, I'm just repeating what I said, but it's great to repeat because then you remember. The actual terms and posting list are only at the leaves right here in blue, and this is where the plus, what the plus means. Okay. Now, this here is a 2-4 B tree. And again, I'm giving you the example, there is no plus in there. The fact that there is no plus means that we have the terms everywhere and the posting list. That's a B tree. And 2-4 means that we have between 2 and 4. So here we have 4, here we have 2, here we have 2, and here we have 3. So this is all good. That's an example of B tree. The plus in there actually means more than just the fact that the terms are just on the leaves. If the terms are just on the leaves, it means that you can do something pretty cool. You can actually traverse the entire list of terms in a linear time. And how do you do that? Because we actually like to put extra pointers in there. So that's the magic. It's like a hybrid structure between a B plus tree and the linked list, actually, because actually this is a linked list. So you see, we have a linked list structure on the actual leaves. So somebody who wants to traverse very effectively the terms without having to go up and down, they can directly use this list structure. Actually, I'm pretty sure it's a doubly linked list because I think there are cases where you might want also to go the other way, right? But anyway, they have extra leaf pointers that make navigation super efficient. All right. So I said between 3 and 5, right? Between 3 and 5 children. Well, in general, it doesn't have to be 3 or 5. Actually, it's never 3 or 5. Well, it's 3 or 5 typically on course slides, because on a PowerPoint slide, it's easier to display with 3 or 5. But of course, you don't get an entire disk block with just 3 to 5. So in practice, it's actually much bigger than that when you do have a real implementation. And you can actually adjust these values. You can just pick anything of the form d plus 1 to d plus 1. So that means if d equals 0, that's a 1, 1 b plus 3. That's totally ridiculous, like a 0-dimension vector space, if you want, totally useless, but it has the merit of existing in theory. Then we have d equals 1, we have between 2 and 3. Then d equals 2 gives you 3, 5 b plus 3s. This is the example that I gave you, the 3, 5 b plus 3, right? But then you also have the 4, 7 b plus 3 and so on. And you can have, for example, the 101, 201 b plus 3, right? And that actually resembles a bit more the one you would have in practice with more keys and more children. All right, so these are the parameters. And now I have to warn you, if you look that up on the internet, you will find people who don't use the d plus 1 to d plus 1 form. They use the d2d, or, you know, there's basically variations, but very roughly, as a rule of thumb, this is roughly double this, right? This is roughly from simple to double, the interval. But there might be different conventions with the plus 1, not plus 1, and so on and so on. So just be prepared for that. But for the convention right here in this course, I'm taking d plus 1 to d plus 1 for the number of children, right? Okay, now a warning. A warning. That's actually a warning that I first saw in a children's book with my grandparents a long time ago, because there was actually fancy drawings in there that you could add colors to. But it was basically a fact of life that if you have here n trees, 1, 2, 3, 4, 5, 6, n trees, how many intervals do you have between the trees?
Yeah, n-1 from also the room and the chat.
Yeah.
And I see also n factorial as well.
Oh, that would be combinatorics. No, n factorial might be a little bit big for that. It is indeed n-1. Right. Okay, but it's always nice to, it's always worth trying and giving an answer. By the way, do you know, I don't know if you ever saw the talks by Professor Manu Kapur at ETH on productive failure. He basically explains that the way you learn the most is by making mistakes and giving a correct answer. This is how you learn. So this is just to repeat, you should never, ever hesitate to always give an answer, even if it's not the correct answer, try it out. This is how you learn. So I really encourage you to never be afraid of always giving answers and of learning. All right. And factorial would be the number of ways you have to reorder the trees, right? So if you want to find the total number of ways to order them, that's n factorials. I see you like factorials. We'll have plenty of factorials a bit later in the lecture when we look into probabilistic information retrieval and language models. There will be factorials all over my slides. So I'm pretty sure you will love that. Okay. So n-1 intervals between entries. So that means, and now I'm coming back to what I said earlier, 3 children means 2 keys. 4 children means 3 keys. 5 children means 4 keys. So this is why, if I roll back where we were, where was my 353? Oh, that was my 353. So you can see, if I have between 3 and 5 children, where was that? I don't know. I thought I had a slide that actually doesn't seem to exist. So I was trying, oh, yeah, it was here. Yeah, here, I remember. So between 3 and 5 children, that means between 2 and 4 keys. So if now you count this instead of counting the children, 3 is between 2 and 4, 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 except the root that has just 1. And this is fine because, as I said, the root can have less. All right. Now, so if we have between d+1 and 2d+1 children, and you probably wondered where do the +1s come from? Well, this is actually because if you look at the keys, this is between d and 2d, right? So it's simple double for the keys, and then d+1, 2d+1. There is another convention of B-tree or B+trees. Instead of giving the interval of children, they give the intervals of keys. And this is how you get headaches, because then you're completely lost. Oh, do you count the children? Do you count the keys? And so on and so on. So if I tell you a 3, 5 B+tree, in my book, that's the number of children between 3 and 5. For some other people at some places on the internet, they mean actually between 3 and 5 keys. And that actually means between 4 and 6 children. All right, but I hope now it's clarifying and at the same time telling you there's different conventions. All right. Okay, now I have an animation to show you how B+trees actually live their life and why this interval is actually here between d+1 and 2d+1. So let's just go through the animation. What I'm going to do is I'm going to insert one by one and in increasing order. It's actually a bit of a special case, right? It doesn't have to be in the increasing order, but let me do it that way just for the purpose of the animation. So this is a B+tree. Let's take, I think, a 3, 5 B+tree. I think I took in there. We start with just the root because there's only one node, right? So there is no depth at all. There is only one node. Then I insert 2, I insert 3, I insert 4, and now I insert 5. But now we have a problem because we said that it's a 3, 5 B+tree, and that means there's between 2 and 4 keys in there, but now we have 5 keys, right? So this is not okay. What do? I split it in here or in here. Okay, you can choose, but let's split it there. And what we end up with is now we have the left with half of it, the right with half of it, plus we added a new root on top. And here I just picked the leftmost one from the right. So now we are again, we were at 2d+1, and now we are at d+1 here and d here. So this is the magic of this interval, simple to double. It has to do with this, that you split them in two and then you can merge them back when you did it, right? So now we can continue to add 6, 7, that's fine. 8, no, 8 is not okay because now we have 5 keys here. That's too much, so we cut it. And here we go. Now we take 7 as the new separation. Okay, now we have 3, we have 2. Let's add 9, 10, 11. Now we need to split again because we have too many keys there. So we split it here, add the 10. We add, so here I'm basically just fast forwarding. So if I fast forward a bit, then I add it all the way to 16, right? And now I even added one more node here, 16, 17 is not okay. So I have to split now. But then you see, I only shifted the problem because now I have the problem at the root, that the root is too big. So I need to split again. And this is how you add one more depth. So you see how the more you add, the higher and deeper the B+3 is going to get, right? So this is actually how it works. And you can see that by construction, it's always going to respect the D+1 to D+1 number of children interval, right? By construction, because whenever it exceeds it, you just split it. Now, if you delete, you will see it works just the other way around. So I'm deleting random pieces of the tree here. And here I have a problem because now it's too small. I need between 2 and 4 keys, right? So now this is too little. So I need to merge probably here. Yes, exactly. I'm merging that. But now I have the problem that this is too small. So I need to merge again. And now I'm good. Now I have exactly the right intervals. All right. Any questions? I hope it gives you an idea of the way a B+3 works and looks like, right? Any questions? No questions?
No questions.
All right, perfect. So this is it. This is what a B+3 is. It is absolutely not trivial to implement. This is actually the reason why we will not actually ask you to implement one in the exercise. That would be an entire semester project to implement a B+3 because this is really complex. It looks simple on the screen, but doing it is a whole other thing. All right. So how to store a B+3 now, because of course it's much bigger than on the slides in practice, right? You might have 100 terms in a single block and so on, and an enormous number of blocks here. Well, typically, all of that is going to be on the disk, right? So you only fetch what you need depending on the query, and then you read from the disk just the part that you need. Typically, all of what is in the upper part is in memory. Why? Because it's much faster. So when you do the lookup, you are in your RAM, you're in your working memory, so that's super fast, and you only read from the disk at the very last level when you access the postings list. Now, this here is also persisted to disk, right? This is in case you lose the electricity or your computer crashes and so on, you still have that on the disk, right? But this is only a persistence of that. The first thing you do when you start up your computer is to load that back to memory, and then you do the lookups in memory, right? This is all in memory, and the bottom layers are on the disk. And that is a typical database thing. Even in relational databases, it works exactly in the same way that the upper part of the index or the B+3 is in memory and the lower part is sitting on the disk. All right. Okay, so this concludes the part on the search structures that form the dictionary part of our standard inverted index. And now you know how it works. And you see that it was useful to visit data structures and algorithms lectures and complexity theory lectures, because this theoretical computer science is directly applied in many other places in computer science. All right. Okay, now let's use that, this capability to do range queries. Oh, we have a question, I think.
Is this the reason why we don't want to have the upper nodes to contain information, because it blows up memory?
Yeah, I think so. Yeah, I would say that. That's pretty much it. If you only put the posting list on the bottom layer, then it's all on the disk, and you can fit much, much more in memory from the upper layers if there's no posting list. That's absolutely it. And that's exactly why B+3s were actually invented as a modification of B-trees. All right. And what I'm saying does not only apply to information retrieval, it also applies to a relational database. Okay, so now let's look at another kind of queries that we haven't seen so far, wildcard queries. Wildcards are when you use the star to mean any characters. So concretely, so here it could be any of that, right? But you rarely write that query directly because that would match anything, right? What you do in practice is you say, okay, Z star Rick. So this allows, in that case, multiple spellings because you know there's many ways of spelling Zurich. There's the English way, there is the German way. There is, you know, that in German you can actually replace the umlaut with an E, yeah, that's another spelling, right? So for this purpose, you have the wildcard. And of course, now that we have expanded our query language with more features, the ability to add a wildcard, we need to implement how to answer that query now, right? So that's the next challenge that we are going to take. So now the wildcard could also be at the end. For example, informat, that's for word families, informatics, information, informative, and so on and so on. Right? You can have several wildcards, for example, foo star ETH slash star bar. So now I came up with basically completely random stuff in there, but this is basically the sort of things that could be matched there. That can also be empty, right? The wildcard could also be replaced with nothing. It could be a leading wildcard queries like X, that's economics, physics, mathematics, and so on and so on. Or a trailing wildcard where it is at the end, mathematician, mathematics, mathematical, and so on. So my question to you is, what do you think, given what we have built so far, the indices and so on we've built, which one of these two is the easiest to execute?
What, the one on the bottom?
This one? Yeah, why?
Well, I don't know, no follow-up on that.
Anybody? On the Zoom chat, I think.
Yeah, we also have, I think first there was an answer here in the classroom.
Yes, yes, go ahead.
Here we go, yes. I think we can just follow the tree from the root until we have some math and then take the rest.
Yes, you are correct. You're absolutely correct. That's exactly it. What would be the name of that, of doing that? It's a name I mentioned earlier when we were talking about trees versus hash tables. Do you remember that?
Searching for a range?
Yes, a range, exactly. It's a range query, exactly. So that's exactly it. The idea, oh, I have to click here, is that if you look, for example, for BA star, what you are looking for is actually an interval. It's the interval between BA included and BB excluded. So you just need to locate, starting from the top, right? You just need to go back to locate BA and BB. And then you find the interval, then you can recursively go down, right? So you could basically, for example, one way to do that is to go from the left, and then you can walk your way following these magic pointers I told you about that basically give you here a doubly linked list. You can basically walk your way until you exit the interval, right? So that's one way to do it. So that's basically the way where you walk left to right. And I don't know if this is what you meant on the Zoom chat, but indeed that's how you can do it. Then you stop right there before BB. The other way is top down. Top down because you just go down locating both sides, and then you realize by post filtering when you go down that you refine the actual location that you consider. All right, does it make sense? So this is a range query. Yes, go ahead.
No, yeah, people are shaking their heads. It makes sense.
Okay, so it makes sense. Perfect. So this is called a range query. And for range queries, B plus trees are excellent. Hash tables are not, but B plus trees know exactly how to do range queries. So the answer is, indeed, it's better to have a trailing wildcard for that, because you can just execute a range query lookup on top of your B plus tree. All right, and that gives you the postings list. Now, how do we solve then star AC? Well, the first thing you notice is we cannot just use our B plus tree the way it is, because that's totally useless. But we could build another B plus tree. We could build another B plus tree by just writing everything backwards, right? We just swap left, right. So we write everything backwards, and then we sort, of course, it's no longer sorted now. So we sort things again and rebuild a reverse B plus tree, or B tree or B plus tree, whatever you want. Now we have a reverse B plus tree. It's just that now it starts with the end of the word. It's all mirrored. So now if we have star AC, we look for CA. We just need to reverse the order. And now we do a range query lookup with CA, and we locate CA, CAB, and so on. This is how it works. Right? Now we have the posting list for terms AC and BAC, because again, this is, always remember, this is a reverse B plus tree. So this is all reversed, left and right. So this is actually the term AC, and this is actually the term BAC. All right, so we know how to answer when the wildcard is at the end. So we know how to answer when the wildcard is at the beginning, except that we need to build another B plus tree. That's an extra effort, right? Building a B plus tree is very expensive. So if you haven't already built it, then that's costly. That's the sort of things you do in advance, of course, of the queries. Okay. So you can imagine the speed of Google if it actually beats the index every time somebody enters a query, right? That's of course not what happens. That's something that's done in advance. All right. Now, if I have a single wildcard query, but it's in the middle of the word, then I can rewrite it. That's maybe that will remind you of these phrase search and byword indices right now. But we rewrite that as zu star and star ch. And then we just do two lookups. One that is on the normal B plus tree with the range query on ZU, ZU to ZV. And here we do it on the reverse B plus tree on HC to AD. Right, and then we intersect the two. So this is how we store, we answer this single wildcard query. But do you see the problem here? Let me help you. Do you see the problem? So can you give me a false positive then? What false positive is going to come out of this query if we do it the way that I have just described? Yes, I think I see.
Statics and
yeah, exactly.
A
star A. Yeah. So statics is the here. That would be indeed a false positive, because you see it will both be returned here, and the intersection will keep it. But if you look at the original query, it doesn't match it. The other thing I see on the chat that is indeed correct. That's another example. If you have A star A, then that will indeed give you what false positive then with A star A. Simply A, right? A would be returned both by A star and by star A, and that would also give you a false positive. All right. Okay, so what do? We just need to post filter. We have the intersection, and then we need to come back to the original query and make sure to test again. If it matches the original query, then we get rid of the false positives. Okay. All right, so now we answered wildcard queries using the B plus tree and the reverse B plus tree. Right, that's the new one we introduced. Let me introduce yet another index. So we have the B plus tree, the reverse B plus tree. Now we have the permuterm index. What is the permuterm index? It's actually a fun game. So let's take a word, plant. Now we are going to look at all the permutations. Well, not exactly the permutations, actually the rotations would be more exact to say. We are looking at the rotations, adding a little dollar right there, and then we just rotate the words. So you see $T plan, NT pla, INT PL, and so on. One way to visualize that is imagine you put all of that on a circle, PLANT dollar, and you just rotate the circle. That basically is the reason why it's called rotation. Right? So this is called the permuterm index, right? And we have this dollar. And the idea then is that if you have PL star T, what you do is that you rotate that to make sure that the wildcard is at the end, because we saw that at the end it's easier to answer. Now we are looking for $T PL star, and right there, it's here. You see, $T PL AN. So you see now how we can actually efficiently answer this wildcard query with the wildcard in the middle, because we rotated the letters to get the wildcard at the end. But since we did the same thing for every word in the dictionary in advance, we already have this index. So what's going to happen, this is how I arrived to Plant. What's going to happen is, again, we are not waiting for people to query to do that. We do it in advance. We take every single term in the vocabulary that we use in the standard inverted index, and we compute all the permutations for Plant, for ETH, for absolutely every one of our terms. And then we sort everything and we merge everything into a single list right there in a single very big index. And what we are going to do is again use a B+3 structure. So we put all of that in a B+3, all the rotations of all the terms, but instead of the postings list, we have the original terms. But of course, if you want to optimize further, why don't you also put the postings list, right? Yeah, go ahead.
I simply wonder why the dollar. Any reason? Why we choose
it's only a convention.
Okay.
Yeah, it's only a convention. You could actually use any sign you want. It would just work just as well. It's probably because it's a special character. You know, there's, for example, in some languages, that's a special character for variables and so on. So it's probably because it's unlikely to happen in the middle of a term that you are indexing. The only place that I could see it happening is maybe if you have a finance related book, then you might have dollar amounts. Maybe if you have a computer programming book that is about the language, then you are going to end up with it. But to come back to your question, this is purely arbitrary. It's just some special character that was taken in order to do it. Right? Did I answer your question?
Yes.
Yeah. All right. Perfect. So we compute these rotations for every word. Then we build this B+3 structure. They point to the original words, and we can also, if we want, extend that as well with the postings list, because then we just have everything at the same place. You could also keep it separate. You could just have this structure separately, and then you use the standard inverted index to then find the posting lists for these words, right? So there is a lot of choice in the way we do this. Okay, so now we have the permuterm index, and the way it works is that you basically build the B+3 in that way with all the possibilities, and then you point to the words. There is one more possibility to do that. It's yet another index that's called the K-gram index. That is in order to solve these sort of queries. The idea is when we have a word, I'm again using the dollar, but this time I'm putting a dollar at the start and at the end. So the 1 grams, that's basically all the letters. The 2 grams, it's basically a sliding window, you know, just like the bywords actually that we saw earlier. We slide a window and we take 2 letters, 2 by 2, 2 by 2, 2 by 2. But again, the first one is with the dollar and the last one is with the dollar, right? So it's a sliding window where we added 2 guards, $2 guards on each side. So then you have 3 grams, 4 grams, 5 grams, and so on, right? Again, this is very similar to the byword and 3-word and 4-word indices that we saw earlier, except that now it's not about words, it's about letters, right? But otherwise, it's the same idea. So now when we do these k-grams, the idea is that typically this is totally useless, letter by letter. It doesn't bring you very far. That would be an extremely small index, actually, because there's very few letters. And these are also too big. It's basically the same idea with the by word, 3 word, 4 word, but when you go too many words, then you have this idea that I told you that it's very long and not very broad. So this is the sweet spot. We like 2 grams, 3 grams, 4 grams. This is typically where we like to look. So what happens is that you can build for 2 words the 3 grams in that case, and you do it for every word, and then you merge it together, and then you build again what is called the k-gram index. It's again a B+3, right? So we had the original B+3, the reverse B+3, we had the permuterm B+3, and now we have the k-gram B+3, right? And again, that points to the words that it actually came from. So you see, it can be a list of words because TER is actually common to the 2 words, right? But we do it with all the words, right? All merged in a single k-gram index. And now what happens is that if we want to query for wildcard, wildcard, we just look for COM here, and then we know there's computer. Maybe there's other words that contain COM, right? So this is the k-gram index. CO star TER, we just look for $CO, right? $CO, TER, right there. And we would also have ER dollar that we could also look at, right? Okay, this one actually, I could actually also have included this one. That would have been fine too, right? So now we can look at computer, Terran, computer, and then we compute the intersection as we did before in order to find those that satisfy this query. And we located all the words that can possibly match this query, right? So you see, we have a lot of tools here, right? We have the B+3, the reverse B+3, the permuterm index, and the k-gram index with k being 2, 3, 4, right? Any value but 2, 3, 4 in general. All right? Okay, any questions?
We have one. Just a second.
Okay, it's me again. I just wonder, in practice, how many of these indices are pre-calculated, like every day, or how is that done? Or is it really just random, everyone decides on its own?
So this is about, now we are basically zooming out, right? This question is actually orthogonal to specifically these indices, but these are very important questions that you have to ask yourself as part of the entire system that you are building. You need to ask yourself, which index do I build? Maybe not all of them, right? Maybe I'm going to build this one and this one in this one, but not that other one. This here really depends on what you expect that your users are going to need, right? In a database, actually, the user itself can even decide what indices to build. But you know that then they have to wait for an entire night until the index is built, right? But basically, the user can trigger the index. So this is one way that a system can do it, to let the user decide. But typically, if you're Google, you're not going to ask your users to ask for indices, right? Then you have to do it yourself, and then you have to make decisions. That depends on how many computers you have, how many resources do you have, how much storage space do you have. That basically depends, and then it's a compromise between the response time and the space that you use. Now, in your question, there was another aspect complementary to which index do you build. It's how often do you rebuild the indices, right? It depends which one, right? So if it's the entire collection, like the original standard inverted index, then maybe in practice you want to refresh it, I don't know, every 2 days. So typically a search engine on the web, it's 48 hours, typically the delay until there is a refresh and it's considered. Actually, we'll come back to that later in the lecture because we'll see you can also do incremental updates instead of rebuilding everything, right? So we are going to look into these things. And then you can actually, this is when the collection actually continuously evolves, right? So there is the case where the collection is fixed, it doesn't change. So you just build index 1 and you're done, once and you're done. And there is the case that the collection continues to evolve, and then you have to incrementally maintain the index, right? Now, if you're looking at the per new term index and the k-gram index, probably these ones are going to be refreshed less frequently because the words, there are less words than books, basically, right? So I think you can maybe do it, I don't know, every 2 weeks, every month, maybe even once a year. I guess the system would work just as well, at the cost maybe of false negatives, right? But it's always a compromise to make. If you accept some false negatives until the next refresh, then that works, right? Did I answer your question?
Yes, thank you.
So there's a lot of freedom, basically, in the way you can implement the system. These are all decisions that must be made every time. Okay. Now, spelling errors. You probably notice when you type a search in a search engine, the did you mean, right? So you made a mistake, but actually it finds out which mistake you made and actually suggests a fix for that. So you can always query for corrected terms. So maybe you can try it every time. Actually, Google tends to do that, right? If it thinks you made a mistake, it will just be proactive and directly give you the query for the corrected terms. You could also only correct the terms if they are not in the dictionary, right? So if there's a misspell, but actually even with a mistake, it still exists, then you could say, okay, then I'm not correcting it. You can be even more conservative, and you can decide to only do that if there are not enough results, because then it's likely a mistake. Or you can even be super, super conservative and not even correct anything. You just make a spelling suggestion. You just ask, did you mean this and that? That's the super conservative approach. So how do you figure out the spelling mistakes? Well, that's done with what is called the edit distance. Right. So I'm probably not going to finish today. Let me start a little bit. The edit distance is how many edit steps do you need between two words? For example, you could remove the R and then add the T. And then you transform the word or into the word to. Or you could consider that you replace here R with an O and O with a T, right? So there are plenty of ways that you could consider. In fact, you can try, because we talked about brute force before, you can try to do the absolute brute force search space. Try to all possible ways you can edit one word into the other. So let's try to find all the ways that we can edit to into or. So let's do it recursively. Maybe the last step was that we added the letter O, right? So it's recursively, we go from, so it's the other way around, from or to T, and then we add O, and that way we went from or to to. Or maybe the last step was to remove R, right? So we had or, we remove the R, then we recursively go from O to to, and then we have this. Or that was a replacement. So we basically replace R with O, and then we recursively apply the part to go from O to T. And then you just continue recursively, and then you have all the possible ways that you can edit one word to the other. This is absolutely huge. Here I did it just with 2-letter words. You can imagine what it's going to be if you take longer words, right? So this is absolutely huge. So this is an example here of an edit from or to, or tor, tr, tor, to, and that was this path. Every path in there corresponds to one way of editing. So if you want to look for spelling mistakes, you basically need to go through that search space to compute the edit distance, and you just need to find the shortest one. Right? So you can do it depth first search, brute force in that direction. You can do it breadth first search, brute force in that direction, right? But as you can imagine, very, very expensive. So instead, what you do is, you notice that there are redundancies. So you merge them, you rotate, and you get dynamic programming. I'm going to go to dynamic programming next week, because I think that's enough material for today, right? So thank you very much. I'm going to activate right after this the question to check that you followed what I said. But other than that, thank you very much for attending. I'll see you next week. Enjoy the exercise session, and thank you, Dan, for moderating the lecture. Thank you, everybody, for the interaction with the microphone and the Zoom chats. See you. Thank you very much.